Hi everyone, this is Sunny Kumar from IIT BHU and welcome to my channel Code with Sunny, and today I am going to discuss the topic the Sieve of Eratosthenes, which is our third topic of Algebra Fundamental series of competitive programming. So what is Sieve of Eratosthenes algorithm and why we are going to use it and where we are going to use it? So let's understand this. So let's begin. So what is Sieve of Eratosthenes algorithm? So basically, Sieve of Eratosthenes is an algorithm for finding all the prime numbers in a segment 1 to n using O of n log of n operations. Note that I am talking about a segment from 1 to n. Suppose we have been asked to calculate all the prime numbers in a segment that is starting from 1 up to n, then how we are going to calculate all the prime numbers in most efficient way? So why do we need this algorithm to calculate all the prime numbers in the range 1 to n? Note that we can also use the naive algorithm. That is, naive algorithm is what? Check every number in the range, you can say in the range 1 to n, whether it is a prime number or not. Yes, we can check whether it is a prime number. Or suppose we pick up an element, let's say 5, and how we are going to check that? So we iterate from 1 up to till square root of 5 and check if there is a divisor of 5, then we are going to say no, 5 is not a prime number. And if there isn't a divisor of a 5, then we can claim that 5 is a prime number. But using this naive algorithm will take us a lot of time. Let's we have suppose I'm going to write, suppose we have n tending to, let's say, 10 power 6, and we are going to iterate for every n, then we are going to iterate from every I that is going to belong to 1 up to n. Then you can see, suppose for very large I, that is for 10 power 5 and 10 power 6, I have to start from the very beginning, that is from the value equal to 2 and up to the square root of that. Then that will take a much of time to calculate, to check if that number is a prime number or not. So it may got what time limit exceeded for a large n. So our naive algorithm get TLE for a what, for what, large n. So we need an efficient algorithm to compute the prime numbers in the range 1 to n in the most efficient way. So how we are going to use that? So the very first, that is classical sieve algorithm, gives us the number of prime numbers and what are the prime numbers in the range 1 to n in O of n log of n operations. That is the very best way to compute the number of prime numbers and what are the prime numbers in the given range. So I'm going to explain how we can compute the prime numbers using Sieve of Eratosthenes algorithm in most efficient way. So let's discuss this Sieve of Eratosthenes algorithm. So what is Sieve of Eratosthenes algorithm? What should we are going to do this in algorithm to figure out what are the prime numbers? So let's discuss that. So what should be our approach? Approach for I'm going to write approach for Sieve. Okay, so don't get confused. So what I'm going to do, I'm going to write down all the prime numbers in the range 2 to n first, and starting from an unmarked number. Note that 1 is already composite. I am not going to deal with 1. Mark all proper multiples of 2, that is I am going to begin with 2, which is going to be what, prime number, and it is unmarked yet. So I'm going to mark all its proper multiples. Note that I'm going to use the term proper multiples, so be careful. So I'm going to mark all the proper multiples of 2 as composite, since 2 is the smallest prime number. So I'm going to begin with 2. Each time move to the next unmarked number and, okay, so I've done something wrong. Okay, so each time move to the next unmarked number and mark all its proper multiples as composite. So suppose I have picked 2 as what? Unmarked number, unmarked, and let's say it is a prime also, unmarked prime number, and I'm going to mark all its proper multiples, that is what? 4, 6, 8, 10. These are what? Composite number. Simple. And what should be our next unmarked number? If 4 is already marked as composite, next unmarked number is what? Next unmarked number is 3. So I'm going to begin with 3. So let's analyze this with the help of a diagram, how we are going to complete all these steps. So let's move further. So suppose I am going to list all these numbers. Let's say we are going to deal with up to n equal to 17. You can also deal with for a large n up to 10 power 6. Suppose we have all these numbers. So I am going to denote white cells as a what marked cells. Note that one is already marked as composite, so I'm going to check out. Let's change this color first. So I'm going to pick a green. So let's do this and let's write this as M, that is it is already marked. So I'm going to pick an unmarked position, that is 2, so which is going to be a prime number because it is what unmarked. So I'm going to fill with a 2. Now what I am going to do is I am going to mark all its proper multiples as composite. So what are the proper multiples? What is the meaning of the proper multiples of a number? Proper multiples of a number are those numbers which are divisible by that number but greater than that number. So what are the proper multiples of 2? So simply proper multiples of 2 are, so firstly I am going to fill this with 1, that is 1 is marked. So proper multiples of 2 are 4, 6 as obvious, and 8 as obvious, and 10, and similarly 12 and 14 and 16. These are the proper multiples of what? 2. And I am going to mark all these proper multiples of 2, denoting that these are composite numbers. Now what I am going to do, I am going to pick the next unmarked number. So what is the next unmarked number? You can see the next unmarked number is 3. So I am going to mark 3 as prime because this is the next unmarked number. So again I am going to mark all its proper multiples as composite. So what are the proper multiples of 3? It is 6, it is already marked as composite, and again 9, 9 is not marked as composite, so I'm going to mark it as composite. 12, 15, yes, 15 should also be marked as composite, so let's mark it. Now we have come to the end of my upper bound, that is I have reached the upper bound. So next I am going to check out which is my next that is unmarked number. So note that 4 is already marked, so I'm not going to pick up 4. So let's decide which so this is our next unmarked. Let me denote is by nm, next unmarked number. Okay, so I'm going to pick up 4. So let's fill this one with the prime number because this is my next unmarked number, so this must be prime. So this is what the classical sieve of algorithm says: pick up every time next unmarked number which will be our prime number and mark all its proper multiples as composite. So I'm going to pick up 5. And what are the proper multiples of 5? So simply the proper multiples of 5 would be what? 10, sorry, so I am going to pick up this one. Proper multiples are 10 and proper multiples are 15. So what are these are the proper multiples. So I'm going to mark with all these with composite. These are already marked as composite, so no need to mark it again. So let's move on to my next unmarked what number, which is what? 7. Note that 7 is not marked yet, so I'm going to mark it as what? Prime number because this is my unmarked number. So if this is unmarked, I am going to mark all its proper multiples which will start from 14. Note that this is already marked, and 21 which goes out of the bound, so no need to do that. So I am going to search for next unmarked number. 8 is already marked as composite, so no need to pick it. Similarly 9, 10. So our next unmarked number is 11, so mark it as prime number and all its proper multiples which is next 22. I am not going to deal with it. And similarly, our next unmarked number is 13. Mark it as prime, and no need to go further because it will go up to 26. So no need to go that. So our next unmarked number is 17. So I'm going to mark 17 as prime number. So what we have found from this basic steps, that is each time I'm going to pick up a unmarked number, that is you can say I pick up 2, I picked 3, 5, 7. I mark all its proper multiples as composites. So why this algorithm, classical sieve algorithm, why doing these steps gives the result accurate and appropriate. So let's understand this. So this is our basic steps to perform the classical sieve algorithm to give the prime numbers in the given range. So what about if we want all the prime numbers from 1 to 17? Just iterate in the array and check if the current positions are what are red color, that is marked as some, marked by some variable. You can also denote it. I am going to explain in later how we can implement this. So if these are marked as red, so these are our answers, that is prime numbers. So I am going to pick up these numbers. So let's understand why this algorithm is working and giving the results exact accurate. Note that our idea behind is if a number is going to be prime, that is a number is prime if none of the smaller prime number divides it. Note that suppose 14 is a composite number, so it is going to be divided by 2 and 7, and suppose let's pick 11, then none of the prime numbers is going to divide it because it is a prime number already. I'm not going to make it divisible by any other number. So it is obvious that 2, 3, 5 and 7 is not going to divide 11. So a number is prime if none of the smaller prime number divides it. This is the main logic. Since we iterate over the prime numbers in the classical sieve algorithm in order, so we are already marked all the numbers who are divisible by at least one of the prime numbers. So suppose we pick up 14. So if 14 is going to be a prime number, then one of the prime numbers, at least one of the prime numbers must have to divide it. But or oh sorry, I've said something wrong. 14 is a prime number only if none of the prime numbers is going to divide it, but 14 is going to be divided by 2 and 7. So this 14 should be a composite number. Now hence if we reach a cell and it is not marked by any prime numbers, then it isn't divisible by any smaller prime number and therefore has to be prime. That is 5, 7, you can see any of the prime numbers doesn't divide 5 and 7, which are smaller than the number. So let's understand this also. Suppose we are at 14. You can see 14 is what? Divisible by 2 and 7. That is, there exists an at least a prime number that is smaller than 14, and that prime number is going to divide 14. Similarly, 16. 16 is divided by at least a single prime number which is less than 16. Similarly, 48 and similarly 9. So let's move further in this part. So I'm going to discuss the implementation of Sieve of Eratosthenes algorithm, how we are going to implement this in our code. So let's move to our online compiler. So what I have done is this is a C++ program. I have taken a vector of primes that is going to give us the number of primes, or you can say what are the prime numbers in the given range. Now here I have started the classical sieve algorithm whose time complexity of O of n log of n. I will discuss that also why this has the time complexity of n log of n. Now here is the sieve function. You can see what I have done is I have made the visited vector, or you can say is prime, that is going to that is initialized with true, indicating that all the current numbers, note that I am going to utilize the indexes to mark the numbers, though all the indexes are marked as true, denoting that all the numbers are prime initially. Let's assume that. So now 0 will never be a prime and 1 will never be a prime, so I'm going to mark that with false. Now I'm going to start with 2. Note that 2 is the first unmarked number, that is false. So I'm going to start with 2 and I'm going to use this condition, that is I into I must be less than equal to n. And why this condition works, because squaring till that is going that is traversing our I till square root of n will give us the desired result, that is all the prime numbers from 1 to n. So I'm going to use that fact also. So I am going to traverse my I with 2 up to what, square root of n, and if my current that is current number is an unmarked number, that is prime number, smallest unmarked number, so I am going to pick this number and mark all its proper multiples as composite. Note that I am going to increment every time by I, so that's why this is working for proper multiples. That is, every time I'm going to mark all its multiples as false, denoting that that number is divisible by my current prime number. Suppose we pick up 3. So 6, 9, 12, 15, 18 all should be marked as composite, because these all numbers are divisible by 3. So these numbers can't be a prime number. So this algorithm is going to work in O of n log of n operations, marking all the numbers as composite as well as prime numbers. So how we can get all the prime numbers in the given range? So let's iterate up to n, and if that number is true, denoting that this number is a prime number, so I'm going to push back this number in my primes vector. So this is the main function. I have taken n as 100 for example. So I have called the C function. I have generated the prime numbers. I have printed. You can see prime numbers in the range 1 to 100 are 2, 3, 5, 7 up to 97. So this is the code. So I'm going to share you with this code so that you can use this in your program directly. You can copy and paste this and you can use this. So let's move further in this part. Now, why the time complexity is going to be O of n log of n. Note that the algorithm will perform n by p operations. Okay, I've done written there is spelling mistake. Though note that the algorithm will perform n by p operations for every prime number p. So hence we need to evaluate the expression. What is this expression? This is summation of, that is sum of the values of n by p for every prime number that is less than or equal to n. So sum of n by p for p belongs to 2 to n and p is a prime number. So this will result in time complexity of O of n log of n and space complexity of O of n. Note that space complexity will be of O of n because I am going to use this what is prime vector whose size is n plus 1. That's why our time complexity will remain O of n. Okay, so if you are interested in how this time complexity comes n log of n much deeper, so no need to worry about. I am going to share this reason with explanation in my description section of the video, so do have a look over it for better understanding. Note that I have discussed here the classical sieve of algorithm. Note there is another implementation, another method to calculate the prime numbers, that is sieve in linear time complexity. So this algorithm, or you can say this method, also generates the prime numbers in the given range, but every method, or you can say every algorithm, must have a pros and cons for its reasons. So in for the case of sieve in linear time complexity, we can also build the prime numbers, but here is one demerit, that is space complexity will be higher than classical sieve, and we can also find the number of prime numbers on the type of prime numbers using segmented sieve. That is going to work for very large and even, because I am going to store the memory as O of square root of n, so this will be also memory efficient. So no need to worry about. Now you can focus on classical sieve of algorithm and generates all the prime numbers in the range 1 to n, and I am going to discuss in my later of the videos how we can find the prime numbers using segmented sieve and sieve in linear time complexity. Okay, so this was the basic of how we can calculate or generate the prime numbers in the segment 1 to n using Sieve of Eratosthenes algorithm, whose time complexity is O of n log of n. uh, time complexity. So if you have any doubts, do not forget to mention in the comment section of the video, and the link to the code for this implementation part will be given in the description section of the video. And please do join for my telegram channel for the latest updates, and thank you for watching this video.